Hello and welcome. You are looking at parallel lines and the triangle AngleSum theorem. Now before I begin talking about that actual portion, the AngleSum theorem, I first want to mention all the different triangle types by name. So if you see the name ever, then you know exactly what's being mentioned. And some of these can actually mix and match. I'll let you know what that means in just a moment. Alright, so first we'll talk about the equilateral triangle where all sides are congruent. So these individual tick marks here state that all of these sides have the same exact length. If you're talking about something that's lateral, you are referring to sides or faces of some sort. And here's this bottom one here. It says equiangular, where all angles are congruent. And in a triangle, when they're all congruent at 60 degrees. In this video and in the next video, you'll understand exactly why this is 60 degrees and why in a polygon of any other number of sides, it might be a different number of degrees. But for a triangle, they're exactly 60 degrees. And then a footnote, all equilateral triangles are also equiangular, but you might not be given both parts of information. So if you're given that a triangle is equiangular, and then this side is 6 units long, then you realize, oh, it's also equilateral. You know, ways for them to trick you and do different things. Then there's the isosceles triangle, where one pair of sides, these two sides next to each other, and then their angles opposite them are congruent. So two sides and two angles congruent, but not necessarily all three sides or all three angles. Then there's the right triangle, where one of the angle measures is exactly 90 degrees. So this perpendicular symbol here helps note that. So the right triangle is exactly 90 degrees. Less than 90 degrees would be called an acute triangle. That's what you see most triangles as. In fact, the isosceles triangle that I drew here and the equilateral triangle as drawn are also all angle measures less than 90 degrees. So the only way it's not acute is if it is right or if it is obtuse, where one of the angle measures is greater than 90 degrees. So like that one. And I imagine you see a lot of triangles like that as well. But if one angle measure is obtuse, the other can't be obtuse. They must be acute. And when one angle is a right angle, they must be acute as well, just so you know. And then there's the scalene triangle, which is, again, just like a lot of triangles as well, but very specifically, every angle measure and side length is uniquely different than the others. So for it to be scalene, no set of sides can be congruent, or no set of angles can be congruent either. And so, as I said, triangles can be more than one thing. You could have an isosceles obtuse triangle. So if it was obtuse at this angle here, and then they have the pair of sides congruent, etc. You can have, like I said, an isosceles right triangle. Okay, so you can mix and match some of the terms here, and it'll still apply. Okay, let's dig into the triangle AngleSum theorem. And what it says is that the sum of all three interior angles, of the measures of them, is always 180 degrees. So if I add up the measure of angle 1 with the measure of angle 2 and the measure of angle 3, their degrees will equal 180 when they're all added up. So measure of angle 1 plus 2 plus 3 is 180. And for a small proof, I'm not going to do a 2-column or flowchart proof. In fact, most proofs that you see online will be different. For the sake of all the videos that I've done, including 2 parallel lines and a transversal, I just want to make sure that I throw this one out there so you can see it in possibly a different way. So the way I'm going to prove this is talk about these two angles right here, angles 1 and 2. Both of these are same side interior angles, and same side interior angles are supplementary. So the measure of angle 1 plus the measure of angle 2 equals 180 degrees. Now if I went ahead and added a new line to here, let's give it a different color. Green. If I added a new line and I crossed it through that same portion right there that divides these lines up, I'm going to make the measure of angle 2 equivalent to 2 new angles, the measure of angle 3 plus the measure of angle 4. Okay, so I'm going to erase 2 because that's what 2 was. This becomes 3 and 4. So now we're looking at the fact that the measure of angle 1 plus the measure of angle 3 plus the measure of angle 4 is 180 degrees. That's by substitution. So, like I said, I'm not doing a 2-column proof, but I'm stating my reasons as I go through. Now what you have is a new transversal here with these 2 parallel lines, if you can see that. Try and hide this line for a moment and just look at this one and these 2 lines here. Now what I'm looking at is an angle right here and an angle 5 I can place right there. And 4 and 5, again, if you can hide this line and see this transversal, 4 and 5 are alternate interior angles that are congruent. So the measure of angle 4 is equal to the measure of angle 5 because all alternate interior angles with two parallel lines are congruent. If that's the case, I can substitute 5 for 4. And I'm going to get the measure of angle 1 plus the measure of angle 3 plus the measure of angle 5 equals 180 degrees. Now I know I didn't use the same numbers as I did here or in the same placement, but as you can see, I made a triangle. I'm not sure if you noticed that part. Right here is a triangle. And that triangle adds up to 180 degrees. And no matter how you draw it and how far I draw out, you're still getting that 180 degree thing because, again, same side interior angles and then the alternate interior angles right there. And you'll always get to that proof. I didn't even need to use numbers there except for 180. And it still makes my case. So let's do some examples where we now know that triangles add up to 180 degrees, and you might have to know some other information about your triangles, such as in examples 3 and 2, and 4. Actually, there's some other information. But the first one here, number 1, the only information that they give you are the two interior angles, 65 and 57, and a third measure W, and that's what we're trying to find. So if I add up all of the interior angles, I should be getting 180 degrees. That's your setup. 65 plus 57, I think, is 122. And when I subtract 122 from both sides, I should get, I think that's 58. So W is 58. Don't forget your units, degrees. Right there. Example number 2. Let's use different colors. I have a right triangle, so it was important for me to know that this measure is actually 90 degrees. Right? They don't tell you it. You have to, it's implied. So now I can add up 40, 90, and x, my unknown, and figure out how much that one is. And then 40 plus 90 is 130. So I subtract 130, and I get 50. Okay, that's one way to do it. Now, I want to go back to my previous, two previous slides ago, after we talked about right triangles, equilateral triangles, and the triangle angle sum theorem. Recall that the triangle angle sum theorem states that when you add these up, they all equal to 180. Well, in a right triangle, if one of your angle measures is 90, then that means that your other two angle measures, if these add up to 180 and I subtract 90, your other two angle measures are 90 degrees. So it's important to note, or it's possible to take away some time of what you need to do and state that these two angles are complementary in a right triangle. So when I went back to this example here, I could have just said 40 plus x equals 90. I didn't have to go the full route and say they add up to 180. In the right triangle, if that's 90, these two also add up to 90 because the measures in triangle add up to 180. So I could have just done it that way, subtracted 40 and got x equals 50. I also want to mention before I forget about the equilateral or equiangular triangle, specifically equiangular, is that when they all are congruent at 60 degrees. Well, it's because all of them are equal. If you didn't know what they were, if these were x, then 3x equals 180. Therefore, x equals 60. That's why they're all 60 degrees in a triangle, in an equilateral or equiangular triangle. So I wanted to note that part as well. Okay, back to my examples. Let's do example number 3 here. We have two different triangles here. We're trying to solve for the angle there. We're missing this angle here, but these are vertical angles, so it's important to know when I find the measure of one, I can get the measure of the other. So first, I'm just going to put a little x here to say I have to solve for this angle measure first. And I have these two angle measures here, 20 and 40. So 20 plus 40 plus x, the unknown, is 180 degrees. 60 plus x is 180. Subtract 60, you'll get x equals 120. So if this angle measures 120, so is this one as well. Now I have that second side with this first side to get this third side. So I can now say 39 plus 120 plus y equals 180. and 100, what is that, 59 plus y equals 180, subtract 159, you'll get y equals 21. So this was the one we had to figure out, and we did. These are examples of obtuse triangles right here. Okay, the final one, example number 4, we have to find z. And again, we have kind of the same predicament. We have two different triangles. We also have this angle measure. We have to find out this angle measure. Okay, but we can't do that unless we know some more information, such as this 50 is pretty nice right here to know. But we also have to find out then this, get out of my way. We also have to find this angle measure here as well. Right there. Now these aren't necessarily congruent or anything like that. Make no assumption about these being the same angle measure. We just have to find out one to use the other. So just like before, I'll call this x, we'll call this unknown y, and this will be z right here. So 60 plus 65 plus x equals 180. 60 plus 65 is 125. And subtract 125 from both sides, you'll get x equals 55. So this is 55 degrees right here. This is 50 degrees, and this is y, this unknown. What we now are featuring is a linear, I guess not a pair, a linear trio, a linear triplet. This whole thing adds to 180 degrees when we add all three of them. These aren't a triangle, so to speak, but this is a straight angle right here. So when I add 55 and 50 and y, I'm going to get 180 degrees. So let's set that up. 55 plus 50 plus y equals 180. So 105 plus y equals 180, and y equals 75. Still not done. We still have to find out z. So y is 75 degrees. We know this is 35. Now we can find z. 75 plus 35 plus z equals 180. 110 plus z equals 180. And z equals 70. So there was a little bit of connection work to be done, understanding other principles such as straight angles, vertical angles, right angles, and not much to be done there. But a lot of different examples where it gets more complex. Okay, now I want to talk about exterior angles. This is the last thing, and then I'll do some examples here. An exterior angle, such as this angle 4 right here, it's any angle formed by the extension of one side of a polygon outside of the polygon. So when I extend this side right here to outside of the polygon, the angle that's formed here, number 4, is called an exterior angle. Exterior angles are always supplementary. I'm kind of going out of order here. Exterior angles are always supplementary to the interior angles it's adjacent to. So angle 4 and 3 are adjacent, and they form a linear pair always, so they're supplementary. So the measure of angle 3, this will actually be a part of my proof. I'm just going to go ahead and start writing it. Measure of angle 3 plus the measure of angle 4 equals 180 degrees. So that's also so that's only one exterior angle. I could have made more. Like I could make one and extend it out that way, and I can make one and extend it out that way, kind of running out of room. These could be angles 5 and 6, if you will. But those are also exterior angles. The number of exterior angles is equal to the number of sides / interior angles of the polygon. So in a triangle, there are 3 sides and appropriately also 3 angles, 3 interior angles. And if there are 3 interior angles and the exterior angles are made outside of it by extending the sides, then there should also be 3 exterior angles, 4, 5, and 6 right there. Now, these angles might not be congruent. In fact, they're not unless the triangle's equilateral, equiangular, or equilateral. But you can still find out its angle measure if you know the measures of any of the interior angles there. But even if these guys aren't congruent, one final note is that the sum of the measures of exterior angles of any polygon, not just a triangle, is always 360 degrees. So if I add up, and I think this is going to be a more important note in my next video. This isn't really a highlight of this one, just because we're talking about exterior angles, I want to mention it now. If I add up the measures of these 3 angles, I'm going to get 360 degrees. Very cool. Final thing is the theorem, a theorem about exterior angles. Another way you can find their angle measure besides using its supplement right here is that exterior angles are also equal to the sum of the 2 non-adjacent interior angles. So angle 4 is adjacent to angle 3. It's not adjacent to angles 1 and 2. So the statement that you can make is that the measure of angle 4 is also equal to the measures of angle 1 and 2 combined when you add them up. They're also called remote interior angles, but as far as the vocab that I've been using lately, I'm sticking to non-adjacent. So the proof behind that, using this setup that this linear pair gives you 180 degrees, and that if you add up 1, 2, and 3, you get 180 degrees. You can then start to work around this a little bit. I'm going to use the subtraction property of equality. I'm going to subtract over the measure of angle 3, and I'll get the measure of angle 1 plus the measure of angle 2 equals 180 minus the measure of angle 3 for red. And for green, I'm going to go ahead and subtract measure of angle 3 on both sides. I'll get measure of angle 4 equals 180 minus the measure of angle 3. Sorry for running out of room there. So you see that there are two things that are equal to 180 minus the measure of angle 3. Measure of angle 4 and measure of angle 1 plus measure of angle 2. If that's true, then by substitution, I could say that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2, because they're both equal to 180 minus the measure of angle 3. And voila. And again, I didn't do my 2-column or flowchart proof. I didn't use statements and reasons. I did make statements. I said the reasons out loud. So there's a theorem that's nice to know. And it's not wrong to, say, add these up and then subtract them from 180 to find the measure of angle 3, and then do 180 minus that number to get the measure of angle 4. But you see where you're kind of doing the same work twice. So if you know these two angle measures, you don't need to do anything else to find that one. You can find that one immediately just by adding these two. Okay, I got 3 more examples for you. Let's go ahead and find measure of angle W. Now I will do it both ways. I'll start off by doing the way that is probably ill-advised. I'll go ahead and make this angle X, and I'll say, okay, first let's find angle X by saying that if I add up the angles in this triangle, I get 180 degrees. So X is 60. And then we go ahead and say, well, this is a linear pair, so X plus W is also 180 degrees, and W equals 120. So W is 120 degrees. But you notice where we already found that answer? Right there. So that answer was already found when we added up 70 plus 50. The two remote, non-adjacent, interior angles added up equaled angle W right there. So again, you kind of go backwards. You subtracted 120 to get to 60, then you subtract 60 to get to 120. There's no reason to do both parts, basically. Okay, example number 2, and this time you have one of the exterior angles, and then you're given one of the non-adjacent interior angles, and you have to find the other. So the idea is if you add 80 and y together, you're going to get 110 degrees. So let's find out what y is. You just subtract 80, y equals 30. So not a difficult problem, but this time you're not finding the exterior angle, you're given it. Now I gave you a nice kind of big fat one that have expressions instead of just the variable. We have to solve for the variable. Then I also want you to find the measure of angle FAB. It's this guy right there. So once you find x, you substitute that value in and you find it. So let's add 55 with 3x plus 2. Those are the two non-adjacent interior angles. And then you'll get 13x minus 3. Combine like terms here, you get 3x plus 57 equals 13x minus 3. If I subtract 3x over here, I get 10x. If I add 3 over here, I get 60. So if 10x equals 60, then x equals 6. They're solving for the variable. Now let's find out what the angle measure is of the exterior angle, FAB. That's 13 times 6 minus 3. I don't know what 13 times 6 is. Let's see. 4 is 52, 5, 78. So 78 minus 3 becomes 75 degrees. That's the measure of angle FAB. I could have done a little more and said find the measure of angle CAB. In that case, you can do 180 minus 75 if you find that out. Or you could have substituted 6 into here added these two up and subtracted them from 180, and you'll get the same amount as well, which these would add up to 75, I suppose. But either way, you're fine. And that's it. Fiend.